Hey everyone, if you missed it, I have been quarantined like many of you have experienced or are currently experiencing. And so let's just jump in with the lesson here about light and waves. The agenda for today, make sure you complete the light and waves Ed puzzle, the light and waves required practice, and the light and waves exit ticket as we look ahead to tomorrow and Wednesday. There is another pivot lab to complete, the atomic spectra lab, and also in class you will be working on the electron energy and light POGL, and I will give more information on that on Tuesday and Wednesday. Properties of light. Light is both a wave and a particle. I'll let you look at this for a second. You can see here that it says light is a wave, W-A-V-E, and also a particle, P-A-R-T-I-C-L-E. Light is a wave and a particle. We will focus today on what it means to be a wave. We will not get too much into the photoelectric effect and what it means that light's a particle, but I just want you to be aware that there is this wave-particle duality nature of light. So what are the parts of a wave? You should draw a wave in your notebook that looks something like this. Label the crest or the peak, the trough or the bottom of the wave. Amplitude is the height of the wave from the middle point, and then the wavelength, as we'll define here in a second, is the distance from technically a point to a corresponding point, or the distance from the peak to the peak. So if you need to pause the video for a second to copy that down, please do so. But make sure you're familiar with the parts of a wave. There are four things about waves that I want you to know, at least in terms of definitions. As we just talked about, the wavelength. It's easiest to remember if you choose it as peak to peak, but really one point of any wave to the other corresponding point of the next wave. Wavelength is often measured in meters or nanometers. When it comes to visible light, which we'll be talking about, you'll see nanometers most often, but we also use meters for many different types of waves. The frequency is the number of waves that pass a given point in a given amount of time. How often does this wave repeat? How often do we get a new wave passing a given point? And it's often measured in hertz, which is the amount of waves per 1 second. And so how many thousands of times does a wave pass a given point in 1 second? Energy, all waves are a form of energy, including light waves. Energy is measured in joules, and wave speed. How far does a wave travel in a given amount of time? Wave speed is often measured in meters per second. That's the m/s. So what are some relationships with these definitions as they pertain to waves? All light waves travel at the same speed. That's where we get the term speed of light. It's the same for all types of light. And that speed is 300 million meters per second, or 3 times 10 to the 8th meters per second. To put that into context, if you were to travel at the speed of light, you could go around the world about 7.5 times every second. Another relationship, wavelength and frequency, have an inverse relationship. What that means is that as the wavelength increases, so we get a longer wavelength, then the frequency would be decreasing, so there's fewer waves passing in a given second. Wavelength and energy, they also have an inverse relationship. So again, if the wavelength were to increase, then there would be less energy in that wave. Well, you could think of it maybe being as less powerful of a wave. So what are some types of waves? We categorize light waves based on their wavelength. We look at what the wavelength is. That's something that we can measure. And we come up with terms for light, like visible light is the light that we can see, the colors we see. And it's interesting to think about that red, right, red over here, where does red stop being red and become orange? And so this is a spectrum, right? It's a full spectrum where there's no gaps. And so this is a complete spectrum of visible light. And so we loosely categorize them as reds or oranges or yellows or greens, because where does that transition actually happen? But there's a lot of other types of light out there that we can't see. And when we combine them all together, we get the electromagnetic spectrum. Visible light, the red to violet. Notice red has a very long wavelength compared to violet, 700 nanometers compared to 400 nanometers for violet. But that's a very small portion of all of the light that we have. If we go to the left of red, we get infrared, then microwave, and then radio waves. Radio waves have a very long wavelength, which means a very low energy. Right, red has a very long wavelength, so it's a low energy compared to violet. So it's all in comparison to another type of wave. From violet, if we continue on and we get a smaller wavelength, more energy, you will have the ultraviolet spectrum, and then X-rays, and then gamma rays have the smallest wavelength, the highest energy, and so we say, or often say, the more powerful waves are gamma rays. So you should understand, take a minute, again, pause if you need to, but you should understand that radio waves have a very long wavelength, and then there's microwaves. This transition, again, it's a loose category that we use, so it's not necessarily a specific definition, but long wavelength radio and then micro infrared. You should understand the order of the visible spectrum: the ultraviolet, X-ray, gamma ray. So that order, what has a longer wavelength, what has a higher energy, you should understand those parts of the electromagnetic spectrum. So chemistry is the study of matter. So what does light have to do with the study of chemistry? Well, our understanding of matter, and atoms specifically, has been greatly enhanced when we started looking at light. That's because atoms can both absorb light and emit light. When we look at atoms, they can have an emission spectra or an absorption spectra. The emission spectra is if we take a substance and we heat it up and make it warm and make it excited, we can then pass that light that it emits through a prism, and it's emitting these specific bands of light. An absorption spectra would be if we were to take white light, pass that white light through the substance, through the gas, and then continue to pass that light through a prism, and you'll notice that instead of being a continuous spectrum, some of the light has been absorbed and is missing. Notice that an emission spectra and an absorption spectra, if you were to overlay them together, you would get a complete spectrum. And so because of that, we often just look at the emission spectra rather than looking at both. So here's some emission spectra. So again, we have a continuous spectrum up top. There's no gaps. And beneath that, you will see 4 different emission spectra: sodium, hydrogen, calcium, mercury. And just take a minute and look at those. And you'll notice that they're all unique, because an emission spectra is like a fingerprint. It identifies the elements. And this is actually how helium was discovered. Helium was not discovered on Earth. Helium was discovered first in the sun, because we looked at the light coming from the sun and noticed that there was a new emission spectra that we hadn't seen before. So there must be a new element, and that element was named helium, and helio is the Latin word for the sun. And so each emission spectra, each element, has a unique emission spectrum. Notice there's some similarities, but you have to look at the whole spectrum to see that it is a unique element and that the emission spectra are unique. And so next time, we'll look more at the emission spectra. And so in the lab, whether you're cohort A tomorrow or cohort B on Wednesday, you will be doing this atomic spectra lab, looking at how we use emission spectra to identify elements. And in class, you will be doing the electron energy and light POGIL, so that we can see in more detail how the emission spectra are formed with the electrons. So now I would like you to complete the light and waves. If you're in class, the light and waves required practice, but make sure you also complete the light and waves Edpuzzle video and the light and waves exit ticket. Please email me if you have any questions, and you can always go back and watch this video to pause if you need to write anything down. But that wraps up the lesson for today.